So let us restart with the Flynn's classification. So as discussed in the previous lecture, instruction stream refers to the set of instructions that are executed, and the data stream refers to the data that is being accessed. So we define the terms S and M, S for single, and M for multiple. So SIST is single instruction, single data, MIST is multiple instruction, single data, and so on. So let's discuss these four paradigms. So SIST is a standard uniprocessor, a standard processor, a standard pipeline that you have studied in chapter 9, which means instructions come from a single source. There is a single process, single thread. Data comes from a single source, and then the program executes. So this is pretty much a non-starter for us. SIMD, also called SIMD, means that one instruction actually operates on multiple pieces of data. So one instruction, an add instruction, will add A, B, also C, D, also E, F. So we'll see an example of this. So vector processors pretty much fall in this category, and we'll discuss vector processors later on, in the same chapter. So they have one instruction that operates on many pieces of data in parallel. For example, one instruction can compute the sine inverse of 4 values in parallel, right? So vector processors can do that. So for the same instruction, multiple data items are actually touched or accessed. MIST is very rare. It means multiple instructions, single data is very rare in practice. So what this is trying to say is that for the same data, multiple programs would be accessing it, and accessing it, processing it. So one celebrated and classic example is an airline system. So in an airline system, what happens in an aircraft? So this rather, instead of an airline system, I would rather make it an aircraft, because that is somewhat more accurate, accurately conveys my idea. So consider a plane, consider an aircraft, right, which is carrying a lot of passengers. So it is possible that a given processor might have a bug, might have a mistake, and that can lead to a failure. So failures in an aircraft can be catastrophic, in the sense that let's say the pilot decides to turn left, but then the computer has a fault, so the computer turns right. Well, it can lead to an accident and a lot of loss of life. So that's the reason what modern aircrafts have is that they have actually 3 processors which pretty much run the same code or the same kind of code. And they actually access the same data, which is the data coming from the aircraft's controls. So in this case, an aircraft can have a MIPS processor, can have an ARM processor, and an x86 processor, pretty much operating on the same data. So the data is the same, but of course the instructions are in a sense different. The reason that they are different is because MIPS has instructions in the MIPS instruction set, ARM has instructions in the ARM instruction set, and x86 has instructions in x86 instruction set. And of course, the same program has been encoded in 3 separate instruction sets, but it might be different programs as well. So different programs which are trying to do the same thing, but just to avoid errors in the program, what modern aircraft companies do is that they assign one team of programmers to write a program and compile it in MIPS. They assign one more team of programs to write the same program, which is to process the flight's data and operate the controls. So at a high level, all the programs do the same, but if different set of programmers write them, you are ensuring that they will at least not do the same mistakes. So they can then write a program for ARM, and another program can write it for x86. So what will happen is that, of course, they become 3 separate programs, but mind you, their objectives are the same, their input and output formats are the same, but nevertheless, they are different instruction streams. So they will operate on all the data that is coming in, which means all the data that is coming in from the aircraft sensors, and then make decisions of what should be done. So let's say in autopilot mode, they might decide to turn left, turn right, reduce the speed, anything and everything. And let's assume that it does happen that one of these processors, suggests a different output. That can be the result of a bug, or a fault in the processor, or a fault in the program that's running on the processor. So what will happen is that the final outcome of what the aircraft should do, let's say two MIPS and ARM say turn left and x86 says turn right. So what they should do will be decided on the basis of a majority vote. So out of the three processors, if two of them say turn left, then we turn left. Otherwise, if two of them say turn right, we turn right. Now this is one of the rare examples where there are different, very different instruction streams, but the data stream is the same, and we are trying to create more reliability via this process. But MIST is typically not discussed. What is discussed is MIMD. So MIMD is multiple instructions and multiple data, which means that we have different programs that are operating on different kinds of data, which you just saw maybe, which you actually just saw in the previous lecture. So in the previous lecture, what we were trying to do is that we were trying to take a large array and we were trying to compute the sum of its elements. The way we did it is that we actually split it into n separate portions, where n is the number of processors, and each portion of the array was given to one processor. So in this case, the data was different, and we had the processors executing different instructions at least at the same point of time. So it is true that they were executing the same program. So what we basically mean by MIMD here is that at the same point in time, the same instruction is not being executed. So it is true that in the examples that we have seen, essentially different threads or different processes actually run the same program, right? And the same program means the same overall set of instructions, even though they are actually different in some cases. For example, in the case of the one on a loosely coupled system, the root node did something and the non-root nodes did something else. But the spirit of the definition is that at the same point of time, are they executing the same instruction or not? So clearly, different processors run at different rates and they can do different things. So clear at the same point of time, they were definitely not executing the same instruction, right? So they were or they were not, but not necessarily. For example, if you have one thread on a slow processor, one thread on a fast processor, it's not necessary that at the same point of time they'll be executing the same instruction. That's the reason you say that they have multiple instruction streams. And also in the case of the loosely coupled system, non-root nodes did something very different and the root node also did something very different. So in that sense, the instruction streams were different. So that's the reason we have multiple instructions. And since all of them focused on different parts of the array, right, one thread focused on this part, one thread focused on the other part, so even the data streams were different. So there are two main types of MIMD processing. One is Spmd, one is Mpmd. So Spmd is basically what we have seen in our previous lecture, which is of course multiple instruction streams, but the instruction streams are coming from the same program. So Spmd means single program, multiple data. So that basically means that the program is the same, but of course different threads can execute different parts of the program. So that's the reason its multiple instructions comes from there. But at least it's the same compiled program and multiple data, multiple data regions. So so this is the OpenMP. So one example of this can be the OpenMP example that we showed, or the MPI example that we showed. So both of them will fall in this category. So here we will typically have multiple processes or threads executing the same program, albeit with different inputs. So the different input in our case was the fact that the process ID was different. So as a result, they ended up executing slightly different kinds of instructions. Not slightly, but in some cases, very different kinds of instructions. So that's the reason it's MIMD, but at least the program was the same. So we call it SPMD. MPMD is slightly different. So in this case, the programs are actually different. So the typical model here is that we have a master program which delegates work to multiple slave programs. And the master program is different and the slave program is different. For example, we will have one master program here and a slave program. The slave programs will be running on the different processing units. They will do their job. And after that, the master program will process the results. So in this case, this program and this program are very different. So of course, the instruction streams are different. And this kind of a model, as an example, was there in the IBM Cell processor, which is at least not in the market as of 2017. So this had a separate master program and multiple slaves. So that's the reason it was MPMD. So what we shall focus mostly in this lecture and what most people actually focus on in SPMD, where at least we have the same program, the same binary, but the binary has different behaviors depending on which thread or which process is executing it, right? So maybe process 0, typically called the root process, has a very different behavior from the rest of the processes. But that need not be the case. That was only the case for our examples. Other examples might be different. So we will mainly focus on this SPMD paradigm. So let's now engage in a deeper study of MIMD multiprocessors, in specific the SPMD paradigm. So let us first look at a logical point of view of how the different processors and memory are organized. So this will be on the same lines as a von Neumann machine, albeit different because we have different processing units. So what we have is that inside the same chip, right? Inside the same physical chip, instead of one processor, we have multiple processors, and each processor has a separate pipeline. So we can have, in this case, let's say n processors. So all of them have a separate pipeline, and they pretty much share the entire memory space as well as the memory structures as well. So all the processors see an unified view of memory, in the sense that if this processor writes to address x, gets x equals 5, and after some time this processor reads the address of variable x, right, assuming that these are multiple threads which share the memory space, it will get the same value, which is 5, right? So whatever was written by processor 1, processor 2 is going to get exactly the same value. Similarly, processor 2 can subsequently write y equals 10. After some time, if processor 1 reads the value of y, it will get the value of 10. So different threads in such a system pretty much communicate via a unified memory mechanism. So this is pretty much the way, this is our abstraction. Of course, this is an ideal situation of what is it that we want to have. In reality, this model, this theoretical model that we have over here, will be implemented with different, will have different implementations. So one of this, so let's first look at what are the main challenges. See, implementing a unified view of memory is in reality pretty difficult. And the reason is that we actually have multiple processors, right? We have separate processors. And these processors might have their own small caches, right? Might have their own, small L1 caches. And then these L1 caches then might be, you know, communicating with a much larger L2 cache. This is one of the ways that we can do things. So pretty much the memory system is not one structure, rather it is many, many structures, right? Where one structure is a cache, there are wires between these caches, right? There might be buffers associated with these wires. So the memory system, just to summarize, is extremely complicated, extremely complex. So it can contain many caches in many different configurations. It can contain many kinds of temporary buffers, as we have discussed in chapter 9. For example, the caches can contain victim caches. The caches can have write buffers. Moreover, it is also possible. So how will you communicate with the memory system? You'll send a message, and a message can be a read message or a write message. So what can happen is in a complicated system like this, there can be many messages that you are sending to the memory system, messages which are in flight at any point of time. So these messages can be read messages, they can be write messages. So many kinds of messages can be sent. Many of these messages would not have reached their destinations. So the entire situation actually can be pretty complicated within the memory system. So it's not a very simple thing as we have discussed in chapter 9. Rather, with so many structures and messages, because reading and writing for somebody who's sitting outside the processor like a compiler writer looks like just a single instruction. But inside pretty much the processor from the MA stage needs to issue, let's say, a read instruction. This will go to maybe one cache. Then the cache might send it to a victim cache. The victim cache might send the request to one more cache. And if you consider write buffers and other things, the entire sequence has many messages. So as a result, the entire situation is pretty messed up, pretty complicated. Also, if messages are sent, messages can be reordered. Even if one processor sends two, well, in our system it's not possible, but in other systems it's possible. But let's consider our simple pipeline that we have. If you have two processors and both of them send out, one sends a read at one point of time and the other sends a write at a roughly similar point of time to the same address. If I run the same program multiple times, it might happen in one set of runs, this read is before this write, and in one more set of runs, this write is before this read. So you can actually get different values. So let's assume that the initial value of x is 0, and then processor 1 issues a load instruction for x, right, for the address of x, and processor 1 issues a store instruction for x. So depending upon their mutual order, so let's say you're trying to store 5 in x, right? You're trying to write set x equals 5. Depending on the mutual order of the messages, you can either read x here to be 0 or 5, right? So the behavior will be non-deterministic, basically because we have many entities that are working in parallel, and since we cannot replicate all the conditions before each run, what will happen is that particularly in this case, where we are trying to read and write the values of the same variable, we can have non-determinism in execution because these messages, their order is not defined. The order is defined for messages from a same processor, and that also not necessarily, but across processors the order is definitely not defined. So we can have a reordering of messages, and that will cause different behaviors. So, characterizing the behavior of a memory system of a shared memory system is difficult, but it is broadly divided into two subclasses, right? So one such subclass of, one such category of behaviors is the behavior of the memory system with respect to access to one memory location. This is the same example I was giving here, that one processor is to read the value of the variable x, and the other processor is trying to set the value of the variable x to 5. So if I consider one single memory location, one global variable, then the behavior with respect to that variable is known as coherence. It's also referred to as cache coherence, but in general coherence. So let's consider some examples, but here are the assumptions we'll be making for all the examples. that all the global variables are initialized to 0. So let's make this assumption that all variables are initialized to 0. And all the local variables which are most likely stored in registers, so let's assume that they are stored in registers, right? They are not stored in memory locations. So let they start with a t. So in a variable like t1, t2, t3 and so on are local variables, they are not global and they can be stored in registers. So let's see. Let's consider this simple example where I have a thread 1 and I have a thread 2. Thread 1 is writing 1 to x, and x in this case is a global variable. So thread 1 is trying to set it to 1, and thread 2 is trying to read the value of the same variable x and put it in a temporary variable, a local variable. So I would rather say local, temporary is the wrong word. A local variable that's saved in a register, and let this be called t1. So recall our convention, all local variables that are stored in registers are prefix start with a t. The rest of the variables start with other letters. So the first question that we ask is t1 guaranteed to be 1? Well, so this depends. This depends on the order in which these instructions execute. So assume that the starting value of all global variables is 0. Can it be 0? So the answer is it can be either 0 or 1. And so it depends on what is the relative ordering of execution. So x equals 1 happens first, and then t1 equals. So if t1 equals x happens much later, then of course we will read the value of x to be 1. That's at least what we expect to read. But if let's say this read happens before, so t1 equals x happens before x equals 1, then of course we will read this to be 0. So it depends on their mutual ordering, and we cannot say for sure what the value of x will be. Sorry, what the value of t1 will be. So given this situation, if whenever I write a code of this type, what I'm essentially doing is that this kind of code is defined as a data race. So it's a race for data. In this case, the race is for data x. So in a data race, if I consider the variable x, then pretty much what's happening is that uh, you know this read and this write are pretty much concurrent, in the sense there is nothing to tell us that this write will happen before this read. So read and write is always with respect to a global variable. So of course we are writing to t1, but that's not counted. We are always, so this is considered a read operation because we're reading from x, and this is considered a write operation because we are writing to x. So there is no order between this read and write, right? So they can happen in any order. So in that sense, it pretty much depends. It's possible that while reading this misses in the cache and this hits in the cache. So this can happen faster, the reverse can happen, so this can happen earlier. Anything can happen. So in such kind of a data race kind of situation, we can always get either of the values, the one before this write, or the one or the value of this write. So let us consider one more example. So let us consider thread 1 that writes to x consecutively, x equals 1 and x equals 2. And let's consider thread 2 that reads from x consecutively, t1 equals x and t2 equals x. And x, of course, is initialized to 0, and t1, t2 are local variables stored in registers. So the question that we ask is t1, t2 equal to 2, comma 1 a valid outcome, right? Is this valid? If this is valid, this means that this value is being read here and this value is being read here. So in a sense, either the reads are reordered or the writes are reordered. So but the first question is, should we even allow this kind of a behavior? Is it intuitive? The answer is a clear no. The outcome is not intuitive at all. Because if we expect that x and 1, x equals 1 and x equals 2 have been written in this order by the same thread, then we also expect to read it in the same order, right? There's no reason why we would expect to read it in a different order, right? So this outcome is definitely not intuitive. Otherwise, x would write, thread 1 would write x equals 1 to x equals 10, and sorry, 10, yeah. And T2 might read it in any order if we allow such outcomes. The outcome is not intuitive, so we will not allow it. So the order of updates to the same location should be the same for all threads. All threads should see that x equals 1. If I consider this location x, first 1 came to it. After that, 2 came to it. So since thread 1 is seeing this order, all the threads should see the same order. So what is it that we can conclude from this example? We can conclude that this outcome is something we don't want to allow. And if we generalize this, we can say that the order of updates to the same location or the same variable, in this case x, should be the same for all the threads, or all the threads should see the order of the updation of x to be the same. So in thread 1, x is being updated as 1 is coming first, and then after that 2 is coming. So all the threads, inclusive of thread 2, should see the same order of updates for x. So they should first see 1 and then 2. So this outcome will not be valid. So let me explain this in one more way. So what is essentially happening is that this is the order axiom. So of course, let me look at some other valid outcomes. One valid outcome can be 0 for T1, T2. One valid outcome can be 0 and 2. Why? Well, so basically it is possible that we first have T1 equals x, which means T1 is read as 0. After this, x equals 1 and x equals 2 execute very quickly. And then for some reason the processor gets stalled between this. Maybe an interrupt comes, so this processor gets stalled. And then we have T2 equals x, so it will read the value of 2 over here. So 0 and 2 is a valid outcome. Well, similarly, even 1 and 1 is a valid outcome. Let's see how. Let's assume we have x equals 1 and then this thread somehow gets slowed down because maybe an interrupt comes here. After that, thread 2 quickly issues T1 equals x and T2 as x. In both cases, we will read 1 and 1. After this, if I do x equals 2, then of course nobody would read the value of 2. So what we see is that we can of course read different sets of values. Similarly, we can read 2 comma 2 also if these two finish and then these two begin. So there is no hard and fast rule, and also we can read 0 comma 0, 0 comma 0 if both of these reads execute before these two writes. Recall the definition of read and write in the previous slide. So in this case, 0 comma 0 is also a valid outcome. But it's just that some outcomes, and this is valid because we are still seeing the same order of updates to x. It is just that these two can happen before these two. What is not valid? 2 comma 1 is not valid because we should see 1 and then 2, right? But we can't see 2 first and then 1, so this is not valid. 2 comma 0 is also not valid. 1 and 0 is also not valid, which means first we saw this and then we stopped seeing it. So these outcomes are not valid. So the order is x equals 0 is at the beginning, then 1 and then 2. So I should definitely see some sequence of values where at least the value remains the same or increases. If you see all of these valid outcomes, all of these outcomes which are valid, 2 is greater than equal to 0, 1 is greater than equal to 1, right? 2 is greater than equal to 2, 0 is greater than or equal to 0, right? So basically the order axiom that we are seeing over here, we are in a sense following it with all of these valid outcomes. So let's again look at both of these examples in a slightly renewed fashion. In one example, we looked at a single read and a single write. And we said that, look, there's a data race here. So depending upon the order of the read and write, we can get different values. However, there is one thing that I had not discussed, which I want to discuss now, that let's say set x equals 1. And after a long time, can be even 10 days or, 3 weeks, I read t1 equals x. And let's assume that in the middle, no other thread has changed the value of x. So what is it that you expect? Do you expect this to be still non-deterministic and give you any value? Because of course there's nothing to order this read and this write. Or do you still have some sort of an intuitive expectation? Well, intuitively, if the physical time, intuitively the physical time between this write over here and this read over here is long, is very long, and is sort of tending towards infinity. And from the processor scale, even 2 minutes is infinity. But if I, let's say, wait for 2 weeks, I should ultimately see the value of this write. This write should not get lost. So this is one thing we need to keep in mind, that everything that I write should ultimately be visible to somebody else. And example, so this is intuitive, that we expect a write which, after sufficiently long time will actually be visible to other threads. For example, I can have one more thread here, thread 3, which is writing x equals 2. So in this case, it is perfectly possible that x equals 2 happens first. The value of 2 is seen by thread 2. So thread 2 reads t1 equals 2. And after that, x equals 1 happens at the end. So any such reordering is possible, but what we want is that if you wait for a sufficiently long time and there are no other intervening writes to x, we should read the value 1. Moreover, what we see in this example is as the same thread where there is an ordering, of course, between the updates to x. If this, is seeing this ordering, that I first write 1 and then I write 2, all the threads should see the same ordering. No thread should see an ordering that is not consistent with thread 1's order. So the way we have captured this is with one more axiom called the order axiom, which says that the order of updates to the same location, in this case x, should be the same for all the threads. So if thread 1 is saying that, look, x was first 0, I changed it to 1, and then again I changed it to 2, well, thread 2 should agree with this view. Thread 2 should agree that yes, it can read any values because of course the execution is non-deterministic, but it should never say that I read 2 first and then I read 0, or then I read 1, or I read 2 first and then I read 0, because it's not consistent with thread 1's order. See, if I define coherence, broadly, I'm talking about coherence, I'll sort of reduce the scope to cache coherence later. So coherence has two axioms. That's the way it's defined. It's very simple. Completion and order. Completion means the write must ultimately complete. What does complete mean? Means that it should ultimately be visible to all the processors, right? Ultimately, well, how long? 1 second, 2 seconds, 1 cycle, 1 nanosecond, or 1 year? Well, this is theoretical. So ultimately means ultimately, the time cannot be infinite. It has to be finite. If I write, ultimately, the write should happen. Second is the order axiom, which says that all the accesses to the same memory address need to be seen by all the threads in the same order. So this outcome is essentially not a valid outcome because it violates the order axiom, right? That 0, 1, 2 is the order seen by thread 1, but thread 2 is basically seeing 0, 2, and 1, right? And 0, 2, and 1 and 0, 1, 2 are not consistent, are not the same, so we are violating the order axiom. So let's look at the coherence axioms with a different pair of eyes. So the completion axiom basically means that a read or write message to the memory system is never lost. It always reaches its destination. The order axiom also means that write messages to the same memory location. Well, I should. Okay, there are two ways of looking at this. So let's look at one way. So it says that write messages to the same memory location are never reordered. But I should also say that from the same processor, or they are never perceived in different orders by different processors. For example, let's look at this. Thread 1, T2. T2 is thread 2, T3, and T4. So let's consider some examples. So let's assume that this writes x equals 1, this writes x equal 2. So let's read T1 as x, T2 as x, and again T3 as x, and T4 as x. And of course, x is initialized to 0. So is it possible that T1, T2 is read as 1, 2, 1 and 2, and T3, T4 is read as 2 and 1, right? So of course, see, between this write and this write, there is no ordering. So either this write can happen before this or this can happen before this. But one of them in any execution, one of them would have happened before the other. And then, so let's consider the case of T3. If T3 sees that this write has happened before this, it would read the values as 1 and 2. Similarly, if T4 will also read them in some order. But if you go by the order axiom, what that says is that in a coherent system, all the accesses to the same memory address are seen by all the threads in the same order. So we can not see 1, 2. So 1, 2 basically means it was first 0, then 1, and then 2. And then we cannot see it as 0, 2, and 1. So these cannot be seen for the same execution by different threads. These two orders are not the same, they are not consistent with each other. So this execution is not possible. This violates coherence. Of course, T3 and T4 can, however, see the order to be 0 and 1. So that is perfectly possible. Maybe this executed way back. So this would see x to be 0 and this can see x to be 1, or even it's perfectly possible that you see 0 and 2. So many of these things are possible. But mind you, 0, 1, 2 and 0, 2, 1 are not possible because you are saying one thread is saying that this write happened before this write. Another thread is saying that this write happened before that write. Both of them cannot be true, right? So I cannot say that I'm holding a pen right now and I'm not holding a pen right now, right? I can't say these things. These statements are contradictory. So one of them has to be correct. So that's the reason this is violating the order axiom of the cache coherence of the coherence uh, of coherence. Let's just use the word coherence for the time being. So this is why I say that write messages to the same memory location uh, either by the same processor or not reordered because the processor would see that order, or as I just showed in this example, write messages will not be perceived in a different order. Okay, let me change this. Let me say that are never perceived in different orders. Right, by different threads, of course. So that is implicit. So I'll change this. The final version of slides, instead of reordered, I'll say perceived in different orders. So these two axioms guarantee that a coherent memory system, or a memory system that observes coherence, appears the same way as a single shared cache across all processors, where there is only one storage area per memory word. So here we are sort of going back and trying to motivate the reason for these two axioms in the first place. So let us assume a system where we have all the processors which are connected to one large memory, right? It's not a cache, it's just one large memory. Can be one large cache, but doesn't matter. It's essentially one large structure, right? So if we have one large structure, all the variables are stored inside there. Now if I look at the completion axiom, it means that one processor sent a write, and it's possible that maybe multiple processors sent a write to the same variable. So this structure will order those writes in some way, but if it maintains a queue, this write will ultimately reach its destination cell, which is within here, and perform its operation. If I consider the order axioms, the way that I look at it is assume that there is an external person outside is taking a look at this memory location. It will see the memory location getting updated in same order. And since these processors are also issuing read messages, they will of course get the same order, right? Because there's only one copy of the memory location. For example, that consider the memory location for variable x and consider an external that is just looking at it. So it will first see that x was 0, then it will see, let's say, x changed to 1 and then it changed to 2. Now if somebody says that, look, I was reading x and I read 0 first, of course, and then I read 2 and then I read 1, the external observer will say, no, this is wrong. You could not have read 2 and then 1 because x first from 0 it became 1 and then it became 2. So this is not consistent with the order axiom. So that's what I'm saying, that the reason that the reason that coherence axioms have been defined in this fashion is to make a complicated memory system appear to behave the same way as a simple system does. So something that the readers can try to do is try to prove that a complicated memory system and a simple memory system behave in a roughly similar way if we have the axioms of coherence, but this is of course complicated. Alright, so let me move ahead. And before I discuss, sorry, there's this one more thing I need to add before I discuss memory consistency. So the overall, let me just summarize, for somebody who does not want to get into coherence into deep, but just wants to know what on earth coherence is about. So let's look at a system once again. Let's assume that I have a multiprocessor with multiple processors or cores as they are called. So in one case, the memory system is very complicated with lots of structures and wires between the structures, very complicated. In the other case, I have a same processor, well, similar, where I also have multiple cores, but they are connected to one large cache, right? All of them. There are no sub-caches, no buffers, nothing. And the cache has, space for all the global variables, and every global variable is assigned a unique location. So to an external observer, the behavior of a program on this system and this system should appear to be exactly the same, right? In the sense, he should not see something that is happening here which is non-intuitive. I mean, this is complex and this is simple. So an external observer should see nothing that is happening here is non-intuitive. So what have we seen to be non-intuitive? One is that I, being a processor, issue a write and the write never happens. Well, this will not happen here. And the same memory address should be seen to be updated in the same order, right? So if these are not happening here, then of course the external observer will complain. But if this system, by some means, if it obeys the axioms of coherence, which are completion and order, then the external observer will be happy and he will say that, okay, fine, this system passes the coherence test. So let us now discuss memory consistency, which is similar to coherence but different in a very fundamental aspect. So the aspect is like this, that coherence was behavior across a single memory location, and consistency specifies the behavior across multiple memory locations, right? So the memory locations per se are different. That is the biggest difference. And here also we can have a set of behaviors that are intuitive and a set of behaviors that are non-intuitive. So let us first get a taste for the intuitiveness of behaviors in systems that access multiple variables. So let's consider this example where thread 1 writes to x, x being a global variable, and thread 1 writes to y. So recall that all the global variables are initialized to 0. And thread 2 reads from the global variables, which are y, and x. Alright, so now let's take a look at the pair of temporary variables t1 and t2. What are the possible outcomes, right, which we think are intuitive and reasonable, right? That being very important. So t1 and t2 can both be 0. There's no problem in that. What this basically means that these two instructions, they executed first and subsequently, after some time, maybe for some reason thread 1 got delayed. So subsequently, the instructions of thread 1 executed. So we read T1 and T2 to have 0 and 0. Similarly, it's possible that first we set x to 1, then we execute these two instructions, and then we set y to 1. So in this case, T1, which is equal to y, will read the value T1 is equal to y, right? So that will read the value 0 because y is being assigned here and not before that. So T1 will be 0 and T2, which reads the value of x, that will read 1. Alright, so T2 will be 1. So 0, 1 is a valid outcome because we can interleave the instructions to generate an outcome 0, 1. Similarly, in this case, even the outcome 1, 1 is possible. That is if both the writes happen early and then the two reads happen. So 1, 1 is also possible. So the question now is 1, 0 a valid outcome? Do you think it's reasonable? Do you think it's intuitive? So let's see when I say that T1 and T2 are 1 and 0, what does it mean? So what it means that T1 has read y to be equal to 1. So definitely the ordering has to be x is 1, then we have y is 1, and then we have T1 as y. And so basically T1 gets the value of 1 and then we'll have T2 as x. So then T2 is forced to get this value which is 1. So as a result, if we let's say proceed in the fashion that we are proceeding and we interleave instructions, I mean bring instructions from different threads the way we are doing, then the outcome 1, 0 is not valid, is not intuitive. So it is simply not an output that we expect given our model. So what is our model? We are basically taking one instruction from here, one from here, and we are just interleaving, but we are never changing the order of instructions in the same thread. This is reasonable because the instructions pass through the pipeline, right? They pass through the pipeline in the program's order, and then they are sent by the MA stage to the memory system. So since that does not get reordered, we are not reordering the instructions here. So we see that 1, 0 is not a valid outcome. So essentially what a memory consistency model says is that given a program, or rather given a program, if we run it, given a parallel program, it will have a set of executions, right? A set of ways in which it can execute. So basically the set of executions will have two types. Uh, so it can theoretically have many types of executions, but some of the executions the memory consistency model says are valid and some are invalid. So in this case, all the executions that produce T1 and T2 are 0, 0, 0, 1 and 1, 1 are valid, right? So 0, 0 in this case is valid, 0, 1 is valid, 1, 1 is valid. What is not valid is 1, 0. So the memory consistency model that we have in mind, that disallows 1, 0 and allows these three outcomes. And the way that we are reasoning is that we interleave the instructions in the different threads. So that is the crux of our reasoning, right? So that is how we have defined something to be intuitive or something to be reasonable. So different machines allow different interleavings, allow different outcomes. So it is not necessary that one machine will has to follow a certain logic. So maybe in some machines 1, 0 might also be a valid outcome. So we will see. And but a model basically tells you that, let's say for a program of this type with two threads, what are the valid outcomes and what are invalid. And if a machine respects that memory model or a memory consistency model, then it will ensure that any execution will always produce a valid outcome. So let's do a couple of definitions here. So an order of instructions that is consistent with the semantics of a thread. Semantics of a thread means, okay, let me go back. So basically the semantics of a thread refers to the instructions that are there in the thread, right? So any order that is consistent with the order of instructions in the thread, that is said to be in program order. So for example, if I consider a single cycle processor, it always executes instructions in program order. Or let me explain with an example. Let's say I have an instruction of the form add R1, R2, R3, and then load. So this is instruction 1 and this is instruction 2. So in the program, instruction 1 appears first and instruction 2 appears after instruction 1. So any processor that is executing, this simple two instruction program should actually execute 1 first and then it should execute 2, right? So we can have a lot of instructions, and if I consider the dynamic instruction stream, then what will happen is that we'll have a set of instructions and maybe we have a for loop. So then the loop will go around several times and again it'll come out of that. So we are essentially producing a sequence of dynamic instructions in the program. So this order, which is the program's natural order, right? The way in which an outsider, perceives the instructions to be executed, let's call that the program order. So any order that is consistent with the program order is said to be the program's order. And what is the program order? So consider a single cycle processor, right? The one that we saw in chapter 8. So let's say chapter 8's processor. Or even the chapter 9's processor, it doesn't matter. So what it basically does is it takes an instruction in, or 8 or 9, let me do it this way. It takes one instruction in, and then after some time, one more instruction comes out. So the order in which instructions come in the same order, instructions get executed and leave the pipeline. So this order in which instructions come in is called the program order, right? Because that is the order in which instructions are arranged in the program. And these are dynamic instructions, of course. So if you have a for loop, then you'll have more of these instructions. So out of these, let's only focus on the read and write instructions because they are the ones that go to memory. The read and write instructions can also be arranged in program order. For example, in this case, this instruction is always before this instruction in program order. Similarly, this instruction is always before this one in program order. So what we say is that if we consider a memory system or a memory consistency model, right, we have defined the model of a memory system or a consistency model of a memory system that determines the set of likely outcomes for parallel programs. So this is known as a memory consistency model or a memory model. So let me read it once again. The model of a memory system that determines the set of likely outcomes for parallel programs. Likely or likely slash valid. So all of these outcomes also have to be valid, right? Outcomes for parallel programs is known as a memory consistency model or memory model. So different kinds of memory models are possible. As we saw on this slide, we are essentially reasoning about valid outcomes or likely outcomes like this, that we are saying we will generate all our outcomes by interleaving instructions from both the threads. Since 1, 0 cannot be generated in this way, we are saying that the outcome is not valid. So here what I'll do is I'll also update this slide, have likely as well as valid in brackets. So let us look at a very simple memory model called sequential consistency. And let's again go back to that slide where we looked at the set of valid outcomes. So what we did is we arbitrarily interleaved instructions of both the threads. So one thread had instructions 1, 2, 3, another had instructions 1 dash, 2 dash and 3 dash, we arbitrarily created. So one execution can be 1, 2 dash. Sorry, I'm sorry. Should be 1 dash. Sorry about that. Yeah, one execution could be 1, then 1 dash, then 2, then 3, then 2 dash, then 3 dash. One more execution could be 1, 2, 1 dash, 2 dash, 3. Right? These two could be. So, we can generate a lot of executions in this manner, but every execution has a property which is that all the instructions in the same thread observe program order, right? So they are in the program order. So one is always first, then two, then three. But between them, they can be arbitrarily interleaved. So you can think of it this way, that you take your 5 fingers and try to interleave them. You can generate many possible interleavings, but all of them have the same property, that in any interleaving, 1 dash will come before 2 dash and 2 dash will come before 3 dash. That's exactly what we are doing in this figure over here, is that we are creating many interleavings of instructions. But if you see, this instruction is always before this and this is always before this. So such kind of an interleaving of instructions where the program order is preserved, right? So program order is always within a thread. It's never across threads, right? When this is preserved, it is known as a sequentially consistent interleaving, right? So that's a very old term discovered in is invented in 1978, but this is essentially called a sequentially consistent interleaving. So a memory model that allows only sequentially consistent interleavings is known as sequential consistency. SC, it's called SC, sequential consistency. So in this example, the outcome 1, 0 is basically not in SC, because SC does not allow, it's not possible to interleave the instructions in any possible way to generate this. So this outcome is not allowed by sequential consistency or SC. So what is sequential consistency? Again, it is basically every thread has to preserve its program order. This comes at a cost. The cost is performance. So let's see what's the relationship between SC and performance. Of course, this is an advanced topic, and only a little bit of it will be covered in this course. Most of it should be left for a course on advanced architecture. Nevertheless, let me explain. So let us assume that we are doing two writes, x as 1 and then y as 1. So both of them will enter the MA stage. From the MA stage, they'll go to the memory system. So now the question is that should we actually wait for the entire write to complete, and then for once you know the write is over, then actually execute the next store. So we have been up till now assuming that all our writes finish in a single cycle, but that is not the case, because you have caches. You might have an L1 cache. Below that, you might have an L2. Below that, you might have a main memory. So it is very well possible that you don't find X in L1, but you find it in L2. So should you actually, in your MA stage, and given the fact that this is your pipeline, should you actually wait for X to actually finish its write in L2 and again come back? Or can you do something better? So what a lot of processors would do is that they will send X to the memory system and then execute the next instruction. And the next instruction will be y equals 1, and they might find y in the L1 cache. So in that case, the write to y, in a sense, will complete sooner than the write to x. So for an outsider, he will perceive the order differently. He will essentially perceive the order as first y was updated and then x was updated. So mind you, in this case, of course, you are gaining additional performance in the sense that you're able to reorder these writes and you're not waiting for this write to complete. But yes, it comes at a certain cost. and the cost is that your memory model changes. So mind you, the execution of this single thread, this is not changing at all. This will remain correct. It is just that for an outside process, instead of seeing this X getting updated before Y, they will see Y getting updated before X. So let's take a look at another example. Uh, Let me actually go back. Let me take a look at another example. So let us say that I set X as 1 and I read another variable Y. So in this case also, if you look at the MA stage, then the MA stage of the processor will first write to X. So it might be using the write buffer optimization, where write buffers, basically what they do is that you have this small cache, with maybe 4 entries or 8 entries, which essentially absorbs all the writes. This is because you don't want to, if it's a large block of 64 bytes and you are essentially writing to every variable within the block, you don't want to send 16 writes, 64 by 4, assuming size of an integer is 4 bytes. You don't want to send 16 writes to the L1 cache. So you typically have a write buffer where you collate all the writes for a single block over a period of time and then send it. So if X is equal to 1, this write can go to a write buffer, in which case other threads will not be able to see it. But the read operation can go directly till the L1 cache or even lower and actually get the value of Y. So for any observers, assume an observer who's standing outside this core. That will basically see that this read operation, this is a write operation, it's a load, and it's a read operation. Sorry, write operation is a store and the read is a load. So anybody standing outside would basically not see the write, because the write buffer is a private structure, but rather it would see the load happening first. So it will basically see t1 equals y happening first and x equals 1 happening later. So in this case, you'll have the load first and the store to X later. So it is very much possible that when different locations are concerned, this will not happen again with a single location. For a single location, the rules of coherence will apply, but coherence is not for is not for different locations. So in this case, what we will see is that processors will do some reordering if they need performance enhancing optimizations such as write buffers. So it will appear to another core or any other entity outside the processor that memory operations are getting reordered. Instead of write and then a read, we are having a read first and then a write. But these things are nevertheless complicated. So it's much better to teach all of these things in a course on advanced architecture, not in a basic course. But nevertheless, people should have some idea because multi-core processors are very, very prevalent these days. And even a phone will have 4 cores or 8 cores. So, as I said, sequential consistency will disallow a lot of performance enhancing functions. One is a write buffer, because the write buffer will sort of delay the write. So you will find that if there is a write and then there is a read, it is possible that the read might complete first and the write later. This is not allowed by sequential consistency. So basically, not allowed, so performance will suffer. Similarly, we cannot reorder write operations. If I'm writing x as 1 and y as 1, then I need to finish, so, I have something like this. I need to ensure that this write is completely over before I do this. And it's very well possible that I get Y in the L1 cache and I get X in the main memory. Then I'll unnecessarily have to wait for a long time. So, given these, so I cannot reorder writes. So you will see in an advanced course that there are many, many restrictions that are imposed on a system if it needs to obey sequential consistency. So we need to add a lot of constraints in the memory system to make it sequentially consistent. But so what happens is, fortunately, most of the time, uh, these constraints are artificial, right? So they need not be there. So what I'm writing on the slide is, most of the time, we need to wait for the current memory request to complete before we can issue the subsequent memory request. This is very restrictive and artificial, and most of the time it does not make a difference, which one completes first, which one completes later, and we just have to write our program in a different way. So that's the reason in almost all commercial systems, sequential consistency is not observed. What is rather observed is something called weak consistency. So, there can be many other models, but I'll only discuss two in this book. So weak consistency allows arbitrary orderings, of course, within some constraints. So, it's not the case that if I write x as 1 in the same thread, assume that this is the same thread, right? And then I read x, it is not the case that I will read t1 as 0. That's not the case. I will definitely read t1 as 1 or any later update to x. That is always the case because coherence will take care of it. And also, the single thread, there is an order, so that will take care of it. So this will, this particular case will never happen. But what can happen is that if I write 1 to x and then I read another global y, then for a single thread, it does not matter whether this executes first or this executes first, because anyway, they are to different locations. But to a multiprocessor, it does matter. And this can be reordered. So in a sense, a weak memory model, a weakly consistent memory model, allows such kind of arbitrary reorderings such that we can put in more performance enhancing optimizations. Think of it that way. So in the weak consistency paradigm, where all orderings are allowed, all orderings are allowed, especially when for multiple locations, and single thread correctness is never compromised with. In such a situation, it's a typically higher performing implementation. So that's the reason as of today nobody has sequential consistency, but almost all the big server companies, IBM, HP, they have a very relaxed memory model. Intel and ARM, to a certain extent, their model is not that weak, but we are not in a position to discuss what is that weak and what is very weak. So let's assume, for the sake of simplicity, that weakly consistent means that none of the orderings between reads and writes to different locations are observed. And let's live with this. That'll keep our life easy. And if we assume that a system is weakly consistent but it's actually stronger, that's actually a good idea because that will not break the correctness of our code. But instead, if we assume that a sequential system is sequentially consistent, but it turns out to be weakly consistent, then of course our code might not work. So let's assume that to program in a weakly consistent system, we have two kinds of memory instructions. We will have regular load store instructions, read write instructions. But since ordering is not very strictly followed, we will have some additional instructions called synchronization instructions. So an example of a synchronization instruction is as follows. So we can have a fence instruction. So the idea here is that this fence waits till all the memory accesses before the fence instruction in the same thread complete. Which means that if I have a set of reads and writes or loads and stores, and then there is a fence, so the fence will wait for all of them to complete. Complete for a read means it comes back with its value. Complete for a write means it goes and modifies the actual memory location. So it will wait for all of this to complete, and then the fence will execute. And any subsequent instruction in the same thread, read or write, uh, can start only after the fence instruction completes, right? So it is like, it's an execution fence in the sense that the fence will not start till all the instructions before it have completed, and no other instruction after the fence can start before the fence instruction has ended. So this basically ensures complete separation of the lifetimes of memory requests before and after the fence. So they are absolutely disjoint. Let us now solve the same problem that we have been trying to solve, and we have given two implementations for it, which is to add n numbers in parallel. So what are the approaches that we have used before this? We have used OpenMP for a strongly coupled system, and we have used a language similar to MPI for a loosely coupled system. But let's look at OpenMP. In OpenMP, what did we do? Well, it was very simple for us. What we did is OpenMP provides a mechanism for a parallel for loop. So every iteration of the for loop runs in parallel. And once the for loop ends and we come out of the for loop, so let's say in a for loop there are n iterations, so n threads are spawned, and all the uh, threads work separately. And once the for loop ends, we assume that all the threads have died, right? They have done their work and then they have all the threads are dead now. So, what is OpenMP? Well, OpenMP is a library. In a sense, it's some amount of code that has been written by somebody else, and that code is being given to us. We are using the features of that code, high level primitives, functions that that code is providing, and we are writing our own parallel program. But being a good computer scientist, is it a good idea to use somebody else's code? Well, often yes, but we should know how it works. So let us try to write a program from scratch, which will not use any OpenMP primitive. We'll just go with whatever language like C or Java gives us, and we will essentially try to write OpenMP. We'll essentially try to write something which we achieved with OpenMP. We'll try to do it without it. So let's see. So let's assume a sequentially consistent machine, because we always need to assume a memory model. Otherwise, our program will not work. So hopefully after an example on a sequentially consistent SC machine and an example on a weakly consistent machine, the viewers of this video will at least appreciate that yes, the programming model is important. So let's have the memory model, I'm sorry. So let's have the same data structures that we had. We have a partial sums array, which stores a partial sum for each thread. We'll have an additional structure called the finished array, which stores the status that each thread is done. We'll have all the numbers that we want to add, the final result, and another flag called done in it. So let's look at the code, and then while looking at the code, all the meanings of all of these fields will be self-evident. So let's do one thing. Let's initialize all the elements in the partial sums array to 0, and the finished flag, all the elements in the finished array, all the flags which are Boolean flags in the finished array to 0. After doing this, let's set done init to 1, which means that our initialization is done. So let's start the parallel section. So let us assume that we have a primitive parallel which ensures that there are n copies of this code running. That is the assumption we are doing. Of course, if we use a library like pthreads, which is provided in Linux, then we just have to replace this directive parallel with one more directive. What that basically does is that uh, creates n threads, and each thread executes the same code. But that would become very, very technology specific, so I've sort of kept it slightly abstract. So we are assuming that this part of the code, n separate threads are spawned, each is running the same. So now it is possible, very much possible, that let's say when uh, the threads start, to ensure that the initialization is done, let's just ensure that done init is equal to 1, because sorry, I think this bracket should not be there over here. So while done init is not equal to 1, we will keep repeating in an empty loop, or we will rather wait for it. Now the question is, why should this happen? Well, the reason this can happen is that in a sequentially consistent machine, it is true that all our memory accesses follow program order. So here what we are doing is that this might be the thread equal to 0, and then we are starting a new thread. A new thread will have its own reads and writes. So technically speaking, this right here and the reads and writes in the new thread, there's no reason why they should follow this because they're not part of the same thread. So they don't have to follow the ordering, right? So what does sequential consistency say? It basically says that given a thread, all the reads and writes in the thread follow the program order, right? So this completes and then we start this completes and then we start this. But now since we are having separate threads, it is possible that we are trying to read something from the partial sums or finished array, and these accesses are not fully done yet because SC does not maintain any ordering across threads. So that's the reason we explicitly set a flag called done init. So when done init is set to 1, it means that by the SC assumption, all the initialization is done. Once other threads see that the initialization is done, they will start. And when is it done? When done init is equal to 1. So as long as done init is not equal to 1, we just keep waiting. And after it is 1, we start. So the algorithm is the same. We get the ID of the thread using the get thread ID call. We have a starting index, which is my ID times size by n. So we're essentially breaking the large array into chunks. We have this exact approach we did with OpenMP, and each one of them starts at a different starting point. Similarly, we have an ending index, which is a start index plus size by n. So we just loop through the chunk of the array assigned to this particular thread and update the partial sums array. And finally, we set finished my ID equal to 1. So finished, recall, is an array of n elements. So current thread just says that it is done and it comes out. So unlike OpenMP at this point, so all of the threads will be over, but one of the threads, which let's say is thread number 0, which started the code, that might or might not, participate in this parallel execution. So it might be one of the threads in this parallel region or might not be one of the threads. But pretty much even if it finishes, even if thread equal to 0 is a part of this and it finishes its work, when it comes here, it needs to wait till all the n threads are done, right? All the n threads are done, okay? And otherwise, it will not be able to proceed. So here is how you wait for the rest of the threads to finish. So this part of the code we did not have to write in OpenMP because it was already written by somebody else. Right? Who is that somebody else? The people who created the OpenMP library. But in this case, since we have said that we'll not take code from anybody, we need to write our own code to find out if all the n threads are done. And so we don't have any OpenMP to rely on. We just have to rely on ourselves, so we can do it. So for a SC machine, it's very easy. We set a flag to 1, and then we simply, so we assume that all the thread IDs are between 0 and n minus 1. That's the assumption that we make. So we just iterate from 0 till n minus 1, and for each one of them, we see the value of this of the finished array entry. So recall that when a thread finishes its work, it sets finished my ID to be equal to 1. So if finished I is equal to 0, this basically means that some thread is not done yet. It's still doing its work. So we set flag as 0, and flag as 0 means we cannot get out. So we break. So do while as long as flag is equal to 0, well, we'll have to iterate. So we again go back. So when is it that we actually get out, right? So we actually get out of this loop when we come here and flag is set to 1. So when will flag be equal to, so that's when we'll exit this do while loop. And when will flag be set to 1? It will be set to 1 when we never enter this part of the code that sets flag to 0. And we enter this part of the code if for any of the threads finished I is 0 or it has not completed. So when all the threads complete, this if statement will always evaluate to false because all the threads would have finished. So we will not enter this part of the code. So while coming here, our flag will be 1. So we will exit the while loop, which means at this point, all the parallel threads have died, right? So at this point, you are sure that all the results, all the partial sums are computed, right? And all the parallel threads are dead, and we just need to add the partial sums. So recall that we didn't have any necessity of actually having this piece of code in a machine with OpenMP. But here, since you're not using any library, we need to write it. Furthermore, since this system has sequential consistency, when we actually read finished I to be equal to 1, which means that this statement has executed, we are sure that the partial sums has also been correctly computed and written to in memory, because within the same thread, SC does not reorder instructions. So if this has executed, means that all of the updates to partial sum are also done. So once we see that a thread has finished, we will automatically be sure that all of its partial sums have been computed correctly. Well, then what? Then life is easy. We then compute the final result, which is just a simple pass through the partial sums array. We just add all the partial sums and we have the final result. As simple as that. So as we see, a difference from OpenMP is like this, that this entire part of the code where we actually checked if each of the entries is done or not, and then we waited. This was hidden from us. It was taken care of. Also, when we waited for the initialization to be done, and why did we have to wait? Well, we waited mainly because, we are not sure that all of these things are done. Uh, the main idea is that this creation of the parallel thread and the write could have been reordered. We didn't want that. Even on an SC machine, we didn't want that. So what we wanted is we are sure that all the initialization is done and then we start. And since the machine is sequentially consistent, if this instruction has executed, all the memory instructions before it would have completed. That's all. That's the main change. It's only at the beginning of the parallel for loop and end of the parallel for loop. The rest remained exactly the same. And finally, we produce the result.